We now want to begin to relate the voltage to other possible variables, and the first variable we want to take a look at is delta G, which is Gibbs free energy. On the screen there you can see an equation that relates the delta G of a reaction to its e to the 0, to its voltage. And keep in mind that in order for a reaction to be spontaneous, the delta G must be negative. And we've already previously discussed the fact that in order for a reaction, redox reaction, to be spontaneous, the voltage must be positive. So what we're going to do is attempt to look at the zinc copper cell and apply the delta G equation to it. Now here's the zinc copper cell with the correct voltage calculated. So that 1.10 volts then would be substituted in there for the e to the 0, which is the generally accepted variable for voltage. We would then also put in the number of moles of electrons, and again the variable n is used for that. And if we look at the zinc copper cell, zinc goes from 0 to +2, which is a change of charge of 2, and then copper goes from +2 to 0, which is also a change of charge of 2. So essentially in this reaction, 2 moles of electrons are exchanged between the zinc and the copper, so we would then substitute 2 in for n. Now the F is Faraday's constant. Faraday's constant has a value of 96,485 coulombs per mole, so that would go in for the F, for the Faraday's constant. So if we place all those values into the equation, we get delta G is equal to negative, there's our 2 moles of electrons being exchanged, times Faraday's constant, 96,485 coulombs per mole, and then there's our voltage from the reaction, 1.10 joules per coulomb. Now what we've done here is we've taken the unit voltage, and the voltage unit is actually a simple unit made up of more complex parts, so we can actually substitute in place of voltage the unit joules per coulomb. So when we do the math here, we end up with a value of negative 212,267 joules. Now it's negative, so that means this particular reaction is spontaneous. Notice that there's been a conversion to kilojoules, because just like with delta H, when the value of delta H is really large in joules, generally that value will be turned into kilojoules, because it just makes the number a little bit easier then to read and to look at. So that's the relationship between Gibbs free energy and the voltage in a reaction. Now we also want to take a look at the relationship between the voltage and the equilibrium constant and the reaction quotient, the Q. Whenever we do a reduction potential problem trying to calculate the voltage, those voltages that we take from the reduction potential table are assuming a concentration of 1 molar for all the solutions. Now what happens if we happen to be doing a reaction where the concentrations of the solutions in the electrochemical cell are not necessarily 1 molar? That's where the Nernst equation comes in. Notice there's an E with no 0, that's the non-standard voltage. And that non-standard voltage is calculated by taking the standard voltage. So you would literally go to a reduction potential table, calculate the standard voltage, and then notice there's almost like a correction factor. That's the RT/NF ln/Q. That whole thing takes that standard voltage and kind of corrects it for not being under standard conditions, and specifically not having solutions that are at a concentration of 1 molar. Notice the R value there is 8.31 joules per mole Kelvin, very similar to the R from the ideal gas law, except that this one is expressed in energy terms. Notice the T there is temperature in Kelvin. The N equals the number of moles of electrons in the balanced equation, so that's like the 2 moles that we used in the previous equation when we were discussing the zinc copper cell. So you would determine the total number of moles of electrons being transferred. And then notice Faraday's constant there again, 96,485 coulombs per mole of electrons. And then notice there too in the equation there's a Q. Remember that the Q is products over reactants raised to the power of their coefficients. for a reaction that is not necessarily at equilibrium. Now we can simplify the Nernst equation to make it much easier to use. And here's kind of the simplified version. At 25 degrees Celsius, which is standard temperature, we've taken the RT and Faraday's constant and combined all of them into one constant, 0.0591. So again, that's the R value, the temperature, 25 degrees Celsius or 298 Kelvin, and then Faraday's constant, and all of that is put into one value. Notice too that we're doing this particular one in log base 10 rather than natural log, so there's also a kind of correction factor in there for that as well. So we're calculating non-standard voltage by taking standard voltage and correcting it by taking the reaction quotient, which is the Q, and the number of moles of electrons. Now, what happens when the reaction is actually at equilibrium? Well, we know the forward reaction and the reverse reaction then would occur at equal rates. And so this is what happens when a battery goes dead. And when a battery goes dead, of course, the cell potential then is 0. So we can take the Nernst equation and we can change it ever so slightly so the non-standard voltage becomes 0. The standard voltage you see there is still in the equation, our correction factor 0.0591 over the number of moles of electrons. And now we can substitute K in for Q because we're actually at equilibrium. Now we could also take this equation and simplify it just a bit by doing some algebraic manipulation. So you can actually then, with the equation at the bottom of the screen there, you can take the standard voltage for a particular reaction and you can calculate the equilibrium constant. So this, in the laboratory, this is a really simple way to get the equilibrium constant. You just simply measure the voltage under standard conditions, stick the number of moles of electrons in there, and you can calculate the equilibrium constant. So let's actually take one and let's calculate the equilibrium constant from a cell potential. So here's our zinc copper cell once again, and the 1.10 volts have been calculated by using the reduction potential table, turning one of the reactions into an oxidation so as to get a total positive voltage. We're going to substitute 0 volts in for the non-standard potential because it's at equilibrium. 1.10 is our standard potential. On the bottom there you see 2 moles of electrons exchanged, and we're trying to calculate K. Now K is contained within that log function, so I've simplified everything here, and then I need to, of course, raise 10 to the 37.2 power, and I get just a humongous K value. That 1.58 times 10 to the negative 37th means that that reaction is going completely in the forward direction. You really could not have a larger K than 1.58 times 10 to the 37th. And this may actually be so large that it won't calculate on many calculators. It's beyond the capacity. So now, how else would you use the Nernst equation? Well, if you have a cell and the cell is 100% one substance, so it's zinc in both half cells. Now this particular half electrochemical cell, you have 0.1 m zinc plus 2 in the left and 1 molar zinc plus 2 in the right. So they have the same parts but different concentrations. So this is another use for the Nernst equation or its derivatives. Step 1 is to determine which side undergoes oxidation and which side undergoes reduction. Now typically electrons will flow towards the more positive solution. So chances are the electrons there are going to go towards the 1 molar zinc plus 2 simply because there's more positive charge there. So the 1 molar zinc plus 2 must decrease in concentration, and the 0.1 m zinc plus 2 must increase in concentration. So notice that the 1 molar side then is gaining the electrons, and the 0.1 molar side is actually losing electrons. So that kind of makes sense. The 1 molar zinc plus 2 is more positive to begin with, so the electrons, of course, should flow towards that 1 molar solution. So you can kind of just look at the the molarities and determine the flow of electrons there. So we end up then with calculating the cell potential using the Nernst equation. So we want to take that Nernst equation that we have been using all along, and now we want to substitute values in. Now, the number of moles, of course, is still going to remain 2. So here's our Nernst equation. The number of moles is still going to remain 2 moles, so our N is 2. The standard voltage is going to be 0. Standard voltage there is 0 because both reactions are the same, right? Same voltage but opposite in sign. So the zinc is an oxidation, the zinc is also a reduction. Different signs on the 2 voltages. When you add those 2 voltages together, of course, you're going to get a standard voltage of 0. Now, the kind of different part here is the Q. When we look at the reaction there up above, remember that Q is products over reactants, and so we see the zinc plus 2 is 0.1 m, and the zinc plus 2 on the left side there, reactants, is 1 molar. So we're treating this just like any Q or K calculation. So product concentration over reactant concentration. When we plug all that in then, so standard 0 voltage, our 0.0591 constant over the number of moles of electrons, and then we put our Q in there, we find that that particular cell is going to have a voltage of 0.03 volts. Okay, so this is another use for the Nernst equation. You can actually create a cell where the components of both sides of the cell are identical. The only difference is you have a molarity difference between the two. So that molarity difference then will cause an electron flow, and you can calculate the voltage using the Nernst equation.